So chapter 15 in your textbooks has to do with probability distributions. So we're going to look at random things, random variables, quantity that can take any range of values, and sometimes that random variable is discrete, in which case only certain numbers can happen. So for example there, if you roll a dice 4 times, the number of 3s you can get can either be 0, 1, 2, 3, or you could happen to get all 4 3s when you roll a dice 4 times. But you can't get a 3 2.5 times, or 2 3/7 times. So that would be something that's discrete because it can only happen a certain number of times that you can count. There's continuous random variables that can take on anything, right? If I randomly say I've picked a number between 1 and 2, could be any number between 1 and 2. And a probability distribution is looking at, and we're going to be studying those discrete random variables when we can count how many times something can happen and looking at the probability for each one of those. So, for example, you throw a coin twice. What would be all of our sample space here? Well, we could draw a tree diagram. First, you could get heads or tails. Then, after you get heads, you could either get another heads or another tails, another heads or another tails. So if we would list the sample space here, you could get heads and heads, heads and tails, tails then heads, or tails then tails. 4 options. Our probability distribution for this is we set up a chart and we define capital X to be something. In this case, we're going to define X to be the number of heads that you could get. So you decide something within your experiment and define that as X. So if we were saying the number of heads that we could get, and we looked at our probability and our sample space before, it's possible to get no heads, it's possible to get 1, and it's possible to get 2. In the second part, you write, what is the probability that X could equal X? So we write it like this. What is the probability that X could equal X? In other words, what is the probability that you would get no heads? Well, how many in our chart before had no heads? Just the one, the tails, tails. So we have a 1 out of 4 chance of getting no heads. How many of those had exactly 1 head? Well, you see that there was 2 possibilities out of the 4. So I could label this as 2 out of 4, or I could label it as 1/2, because there's a 50% chance of that happening. And the probability of getting 2 heads was 1 out of 4. And what will always happen, since a probability distribution adds up every single case that there is, those numbers there should always sum or add to 1, or 100%. Because you've looked at all the possibilities, and you should get 100% of things happening. So that's what this says right here. We've got for any of the possibilities, the probability of any possibility is somewhere between 0 and 1, or 0% and 100%. And if you add them all up, Have you seen this symbol before? Yes, no? Okay. In math? This is, first of all, this is the capital letter sigma. And in math, it means a sum. Add up a bunch of stuff. So if you add up all those probabilities that x equals x, which we saw before, it'll always add up to 1. Here's a big tree diagram of a coin tossed 3 times. If we stay with the possibility that x is the number of heads that you could get, what are our possibilities? Could get 0 heads, 1, 2, or 3. And then you look through all your sample space and can fill out the probabilities of each one, which forms a nice pattern, which we'll look at in more detail later. So here, a box contains 2 red marbles, 6 green marbles. You choose the chosen at random and then replaced. So 2 marbles are chosen, so you make a tree diagram. The first thing that happens is you choose 1 marble. You've got a chance of getting red or green. The chance of getting red is 2 out of 8. The chance of getting green is 6 out of 8. Then you choose your next marble. Again, you have a chance of red and green. And because the marble is replaced, it's still going to be 2 out of 8 and 6 out of 8. 2 out of 8 and 6 out of 8. Now our random variable x is the number of green marbles obtained. Well, we could get 0, 1, or 2 green marbles. But now our probability distribution is not just based on the fact that there's 4 things, because there's different probabilities for each of those 4 things. So the chance of getting no green marbles would be the first branch, red and then red. And the probability of getting red and then red will be this 2/8 multiplied by this 2/8. So we will get 4/64 as the chances of getting 0 green marbles. Quite unlikely. To get 1 green marble, you can see that there's 2 cases. Either branch 1 with the green or green first and then red. If we actually multiply these things out just so we have the data beside us here, you can see that getting the 1 green marble is that 12 out of 64 plus the other 12 out of 64. So when we write it in the chart, there's 24 out of 64 chances of getting 1 green marble. And finally, the chances of getting both of them green is 36 out of 64. If you want to do a quick check to see if you've done things right, you can add these fractions up. Do they add up to 1? Because in a probability distribution, you've listed all the possibilities. It should always add up to 1. And in this case, it does. So if you roll 2 dice and you want to say their difference, I don't know if you've ever played a game where that's what you would do. Monopoly would go very slow this way. Instead of, if you roll a 6 and a 6, you don't move. You stay exactly where you are. If you roll a 5 and a 3, you go up 2, because the difference is 2. When you get to that guy's hotels, you're going to almost surely land on all of them. And if you land on a hotel on Boardwalk, and you roll 2 6s, you stay there and have to pay again. So it would be very, very dangerous. It would be also a very long game because you would never pass go. Well, you would eventually, but very slowly. So if we look at the differences between the two dice, this is what our new chart or lattice diagram would look like. So once you've done that, I want you to see if you can fill out the probabilities. So X is listed here as the difference between the higher and the lower score. So these are our possibilities that we could get. And then from our probability distribution, we'll be able to see which is most likely. How did you do? So according to these results, if you were playing a game with this, the most likely thing to happen would be to move ahead 1 space. The least likely would be to move ahead 5. And again, those all add up to 1. So I'd like you to try this one on your own. So what do you think? Is this a valid one? And how come it's not valid? Doesn't add up to 1. So if it is a valid probability distribution, those numbers, 0.2, 0.3, 0.4, 0.2, when you add those up, you get 1.1. They do not add up to 1. So no, this is not a probability distribution. So consider random variable x defined with probability of x equals 0 equal to a, equal 1 equal to 2a, and 2 equal to 3a. So what you can do with this data, so again, this is an example of an IB question where the context is taken out. And all we can do is say, well, I can rewrite this as a probability distribution chart. They've told me all the different possibilities are 0, 1, and 2, and the probabilities of each one are a, 2a, and 3a. What do we know about a, 2a, and 3a? They add up to 1. So if those add up to 1, we can set up an equation and we can figure out what the value of a is. Looks like a lot of people are done 9, some are just finishing up. Just check here, setting up your tree diagram. Notice this time that the marble is, or the cube is not replaced. So our probabilities in our second branch are affected by that, as is how many are left in the bag. And then setting up our probability distribution of all of those ones. X is the number of white. Yes? Good? All right, I'll let you work a little bit more on number 10. What I decided to do is I decided to look at Kirsty first, and then Bridget, and then Kirsty getting the job or not getting the job, and then Bridget getting the job, not getting the job, getting the job, not getting the job. I saw some different notations going around. I saw some people put K and then not K, B and then not B, B and then not B. So something that either is really obvious for what you're doing, or when you're showing your work, a little bit of an explanation. So sometimes what might be good is the first time I actually write job, and the next time write not job. And then after that, the abbreviations sort of fall naturally. You could tell what I meant. I was looking over my last year's notes, and I had something like this, and I had no idea what my letters stood for when I last. Yeah, I don't know. Any idea what that? The other one was obviously job, and then this one stood for something that made sense at the time, but only Bridget job. But I had it for all of them, so I have no idea. Anyways, so I switched it to job and not job, because that I think I'll remember. And then once you set up your diagram, I included the probabilities here, so when I went to do my chart, it was easy to see. One of them getting the job is those two middle cases added together. And there's a good chance that somebody will get a job, because there's only a 5% chance that nobody will get a job.